Welcome to another Explainer. Today, we're going to completely transform the way you approach Cambridge mathematics. We're going to take what often look like incredibly dense, intimidating algebraic formulas and turn them into elegant, highly logical frameworks. Think of these frameworks as a sort of mathematician's spellbook, because once you really understand the underlying structure, you can essentially cast the right mathematical spell to solve problems that would otherwise take a lifetime to calculate manually. Okay, let's dive right into this. Here's a quick look at our syllabus for today. We'll start with the magic of patterns, move into the binomial framework, then tackle arithmetic progressions, geometric progressions, and finally, wrap things up by conquering infinite series. Section 1. The magic of patterns and the absolute impossibility of brute force. Let's start with a classic mathematical legend. When the vizier Sisa ben Dahir invented the game of chess, he presented it to the Indian king Shirham. Now, the king was so absolutely thrilled with the game that he asked Sisa what he would like for a reward. Sisa's reply? Well, it seemed incredibly humble at first. He asked for just 1 grain of wheat to be placed on the first square of his chessboard, 2 grains on the second square, 4 on the third, 8 on the fourth, and so on, doubling the amount for all 64 squares. The king agreed immediately. He didn't do a single calculation. He just thought, wow, what a meager request. But as you might have guessed, the king fell into a massive mathematical trap. And this brings us to a really crucial question for you. Given that 1 single grain of wheat weighs about 50 milligrams, what mass of wheat would actually be placed on that board? Now don't worry, we're going to learn the exact framework to solve this without having to manually add up 64 separate numbers. I think Professor Raman Parimilla perfectly captures our goal for today. She says, math has the beauty of poetry, its abstractions are combined with perfect rigor. To solve massive, seemingly impossible problems like the king's wheat, we can't just rely on guessing or brute force. We really need the poetic beauty of patterns combined with the rigorous structure of these mathematical frameworks. But before we get to casting our formulas, we have to make sure we're all speaking the exact same language. First up, a sequence. This is simply a set of numbers in a specific given order. Think of it like a list. But a series? A series is what happens when you take all the terms of that sequence and add them together. That summation is indicated by that large zigzagging Greek letter sigma. So just remember, a sequence is the list, while the series is the total sum. Keep that in mind as we move forward. Section 2. The binomial framework, expanding the impossible. All right, here is our first major tool. This allows us to expand massive polynomials without the absolute nightmare of doing endless manual multiplication. If you take a binomial, which is just a 2-part expression like x plus y, and raise it to a power, the coefficients of your answer will form this staggering symmetrical framework known as Pascal's triangle. Though, fun fact, it was actually discovered centuries earlier by Chinese mathematicians like Yang Hui. Just look at the pattern here. Every number is simply the sum of the 2 numbers directly above it. 1 plus 3 gives you 4. 4 plus 6 gives you 10. It's beautiful, really. This triangle instantly gives you the coefficients you need to expand your expression. But let's be real for a second. What happens if an exam question asks you to find the coefficient for a power of 25? Writing out 25 rows of Pascal's triangle on your test paper would literally take all day. So the crucial point here is this formula, the binomial coefficient formula, which is often written as n choose r. By using factorials, which, if you remember, just means multiplying a number by every whole number below it, you can bypass drawing the triangle completely and pinpoint the exact coefficient you need for any term instantly. It is an incredibly powerful shortcut. Section 3. Arithmetic progressions, the power of addition. This next concept is brilliantly illustrated by a story about the famous mathematician Carl Friedrich Gauss. When Gauss was just a 10-year-old schoolboy, his teacher told the class to add up all the whole numbers from 1 to 100, probably just hoping for some peace and quiet for an hour. But Gauss almost instantly answered 50-50. How on earth did he do that? Well, he definitely didn't brute force it. Instead, he visualized the series forwards and then wrote it backwards directly beneath it. He saw that 1 plus 100 is 101. 2 plus 99 is 101. He quickly realized he had exactly 100 pairs of 101. Multiply those, divide the whole thing by 2, and boom, 50-50. Pure elegance. Gauss's childhood trick isn't just a fun story, it's actually formalized into what we call the arithmetic framework. Any sequence that increases or decreases by adding a fixed amount, which we call the common difference, is arithmetic. To use this framework yourself, you just need to decode these specific variables. Let's break them down. A is always going to be your first term. D stands for your common difference, N is the number of terms in the sequence, and L is the last term. Once you have your variables sorted out, you just plug them straight into these two master formulas. The top one is used to find any specific term in the sequence. And that bottom one? That's the sum formula, which is literally Gauss's trick codified into algebra. With this, you can find the sum of any arithmetic series, whether it has 100 terms or 1,000,000 terms, without ever having to calculate a single tedious step in between. Section 4, Geometric Progressions, the power of multiplication. So we've covered addition, but what happens when our numbers aren't just adding up, but are actually multiplying and growing exponentially? Let's compare them directly on the screen to really see that structural shift. The arithmetic progression we just looked at is built entirely on addition, using that common difference d. But a geometric progression is fundamentally different. It's built on multiplication. To get from one term to the next, you have to multiply by a fixed number, which we call the common ratio, or r. Because we're dealing with multiplication now, our formulas have to change. Notice how the general term now involves raising our common ratio, r, to a power. And take a look at that massive formula at the bottom. That is the geometric sum formula. And guess what? This is the exact spell we need to cast to solve that impossible problem of the king's chessboard from the beginning of our explainer. Remember, on the chessboard, the grains doubled on every single square. So our common ratio, r, is exactly 2. If we go ahead and plug our 64 squares into that geometric sum framework, we find that the total number of grains is 2 to the power of 64 minus 1. That results in a frankly staggering 1.84 times 10 to the power of 19 grains of wheat. To put that completely into perspective for you, that amount of wheat exceeds the entire modern world's annual production of all cereals by an unbelievable margin. The king was literally ruined by a geometric progression. Section 5. Conquering infinite series, summing the endless. Now you might be asking, how is it logically possible to find a finite sum for a series of numbers that literally never ends? It sounds like a trick, right? Well, the secret lies entirely within the convergence framework. It all depends on your common ratio, r. If r is a fraction sitting between -1 and +1, the terms in your sequence are going to get progressively smaller and smaller. They essentially shrink towards 0. And because they are shrinking, the series converges, meaning it approaches a precise, exact mathematical limit. And we can find that limit using that beautifully simple formula right at the bottom. Sum to infinity equals a divided by 1 minus r. Let's actually look at this in action so you can see what I mean. Start with 1, add a half, then add a quarter, then an eighth. Notice how the sum tracks as we add these terms together. It goes from 1.5 to 1.75 to 1.875. As we endlessly add these halving fractions into infinity, the sum creeps closer and closer and closer to exactly 2. But mathematically speaking, it will never ever exceed it. The infinite is successfully contained. But, as a final warning, you must be careful. If you try to apply these frameworks where they don't belong, you will break the rules of math and end up with total paradoxes. Take a look at these alternating powers of 2. 1 minus 2 plus 4 minus 8. Because the ratio here is -2, which is outside our -1 to 1 window, the series diverges. But depending on how you group the terms in your calculation, you can actually trick the math into giving you an answer of positive infinity, negative infinity, or even 1/3. So I want to leave you with this provocative thought. When the rules of mathematics break down into wild paradoxes like this, are we discovering a fundamental flaw in our universe's logic? Or are we just proving that we need an even more powerful spellbook? Think about that next time you sit down to study, and keep mastering those frameworks.